Hi everyone. So this video is about basically a brief comparison between norm penalties, which we have studied so far. So we have taken L2 and L1 regularization, which are forms of adding norm penalties, which is basically penalizing the cost function by an added term that depends on the norm of the parameters, versus using the same function, the regularizer, which we called omega, right? The omega of theta. So that same function, we can use it for an explicit constraint. And what we mean by an explicit constraint is, instead of saying that I add a term alpha times omega of theta, no, I have a constraint that says that omega of theta has to be less than or equal a certain value. Now, let's see what are the differences. One of the major and fundamental differences is that the norm penalty would penalize the norms of the parameters no matter how small they are, right? It's true that omega will be less, right? So the penalty will be small, but it keeps pushing for smaller and smaller weights in terms of the norm. For example, if it's L2 norm, it keeps pushing for smaller and smaller weights in magnitude, regardless of how small they are. So there is no limit at which the regularization function stops, right? Stops penalizing the cost function. So that could be problematic. That could be problematic, for example, by producing local optima, right, with small weights and high cost. So it might, because there is always this continuous preference, right? So it's a continuous cost function with a persistent preference towards weights or parameters that have smaller norm values, regardless of how small they already are, right? So it might do that at the cost of having the unregularized cost high, and it might get stuck in local optima, because maybe the global optima have the parameters, have the unregularized cost much less, but the parameters slightly larger, but not necessarily very large, right? And that's why sometimes it's useful to have this explicit constraint. And basically the explicit constraint saying that as long as the norm less than a certain threshold, then I don't care how small it is. And that solves that problem, right? And at the same time, there is another advantage of this, of having these explicit constraints, is that you know that no parameter, there will exist no parameter that passes this threshold. Whereas in the norm penalty, maybe some parameters will have very large values at the cost of other parameters being very small, right? And that could introduce another problem, which is some parameters overwhelm the learning process, meaning that some other parameters becomes negligible or saturate. They are not learning, they are not updating anymore, right? So the way explicit constraints work is that first you update the weights according to the unregularized cost gradient, and then you project the obtained weights to the nearest point satisfying the constraint, the explicit constraint. So in every iteration of training, first I update the parameters according to the unregularized cost gradient, and then I reproject to the nearest point satisfying the constraint. So the one other advantage related to the reasons we just mentioned is that this strategy will tolerate higher learning rates, because I could have big jumps. The problem with I could have big jumps in the parameter update, and that's what higher learning rate imply, right? So I could update the parameter by a big step, and that's problematic with norm penalty, because that big step could go towards an undesirable place. But here, because I can reproject within the region of the explicit constraint, so there is no such problem, right? So it can enable more exploration of the parameter space while still guaranteeing that I am confined, that every single parameter will overall the norm applied to every single parameter will satisfy the constraint, right? So that alleviates the effect of having, so what I just mentioned about some units overwhelming others, it will alleviate the effect, which is a byproduct of that phenomena, what's called dead units, right? And basically dead units means that some units are not learning. So it's not, all these training iterations are not useful for updating these units. That's a phenomena that can happen with norm penalty because the weights associated with other units can overwhelm the learning process, but could be alleviated with using explicit constraint, right? Now, this becomes very interesting, this explicit constraint with reprojection, when you decide to apply it not necessarily to all the weights in the network, but maybe to weights only within a single layer, or to weights emanating or sinking in a single unit. And in every choice of these will reflect a belief that the importance of a single unit or the importance of a single layer should not overwhelm the learning process of the overall network more than a certain amount. Thank you.